So let's look back to this diagram, so which that is called the fundamental community diagram. So I think some have already explained the philosophy behind this diagram. So let me add a few words. So recall we said there are three ways to control this B-mode on bound G. So Eisenstein thing, which has to do with probonic subgroups. So let's ignore it now. So the other two things, one come from Cosmodi representations, the other come from some Whittaker thing. So ideally, so you may want to say, like this core F must be fully faithful, and this log might be a quotient functor. So in your good word, that would be true, but in fact, they are not true, so they are almost true. So let's ignore this difference. So let's pretend we can prove this is fully faithful and this is like over their quotient. Then try if you want to prove Lagnant's equivalence, you may want to identify the kernel of this functor and kernel of this functor. So and then you win, or you can try to identify the essential image of that functor and the essential image of the gamma stack. You can also win, but in reality, we can do it either. Even worse, we can't prove this guy is fully faithful. So I think on Friday, so Joachim will say it's conservative. And a priori, we can say nothing about this functor. We don't know whether it's a quotient on for log. So maybe tomorrow, if I have time, I will explain. So it's essentially a Verdell quotient. And for this functor, so I think on Monday, the ranking exponent is almost fully faithful. So, but even if you can do this fully faithfulness and essentially subjectivity, you still cannot compare the kernels with the essential image. It's just too hard for us. So, but why can we even prove this geometric diagrams? The reason is we can interplay between these two models and try to play with them and using some categorical way. And finally, at some point, so maybe Dennis and Sam, they realize we have enough information to get to the conclusion, and that's the history. And for today's lecture, so what I will do is I will do this computation. So which is on the G side to compare this Cosmodi and this Whittaker. And then what Kevin will do, Kevin will study this computation.
What's the definition?
I will explain what these functors now you just imagine there are some random categories and these random functors. So and tomorrow, so Nick will explain that the outer diagram commutes and more or less by design. So the lower diagram commutes, which implies the upper diagram commutes. And this establish this fundamental community diagram, and maybe later, so people will show how to use it to deduce the fact that L is an equivalence. This is our roadmap. So let me write down what our current goal, which is very modest. So go now. Let me say our primary goal now is to describe the left vertical compilation, but not in a random way. So look, this source is KL, which is a local category, and this target is width, which is another local category. I will remind you what are the definitions. So both the source and target are local categories, but it factors through some global thing. So you may hope to describe this thing purely via local data, but it's impossible because it factors through some global thing. But so with the help of this run space and all the magic Nick taught us, so it's possible to do this. So I will use the word run magic to refer to whatever Nick taught us in his lectures. And I will present how to describe this computation using pure local data and some nuances. And to do this, there are two steps. Let's not put anything into one reach. So the first step is to describe the following function. So here, this is coef rank. So we actually have seen this function before. So I will remind you what's the definition later. But for now, you only need to know it's a function from from G just to vector space. It's the coef function defined in day one. So this is step one. And step two is in some sense purely formal. So we will take actions and some other run magic to deduce this description from the spectrum description. So this is what we will do for step two. So that's our primary goal. And let me also tell you there are some other goals. So here we are interested in the combination of log followed by coef. So you can also consider other things, like you start from log and try to compose it with some other functors, although we haven't defined it. So you can try to compose with the constant functors, which is some kind of parabolic restriction. And even more naively, you can try to compose with the forget function from D modules to just net the modules to consequent shifts. So you can try to calculate these things, and we will also give descriptions for them. So because essentially, so the description of these things, so is similar to the description of this function. So they can all be described in some pure local data with the help of the run space. So that's our goals. So any questions so far? So okay, so if there are questions, so let's start from some of the connections of the players. Might take like 20 minutes. So first, let's do this KN. So let me remind you what's this KN. So I will be very informal, and I will say this cryptocurrency category at a point is just modules for this type channel pair, as explained in Guber's talk and in Sam's talk this morning. So I will just say a couple of modules for this pair, and recall in Sam's lecture. So we write this function as a function of something. This is function level infinity x. So it classifies G pointers on x equipped with a trivialization as a disk of x function by this output. And it also tells you that there's a loop through action on this guy extending this output action. So often we are removing and using all this action and the general paradigm of localization, we can produce some functor from KL to be more than 1G. So namely, so this action gives you a map between the algebras. So here we can study algebras of this loop proof, which is just loop of this the algebra. So it maps to vector fields, the algebra of vector fields on this function level infinity. So I will just write it as P of x. And because it's a homomorphism between the algebra, it's also it induces a homomorphism between the element of the algebra, and by base change, you obtain the function from this guy, modules for this move the algebra to B modules on this on G level infinity. So by the way, so in this lecture, so we always work with critical level. So I will just make those up, please. So we obtain this function. So then we remind you it's an n for some tensor product here the um as a constant sheets. Maybe of other things. This is u of t. So we obtain this function. Now we can use this L plus G probability to obtain a function from the KL category to the quotient of this functional infinity x by the calculus if we use the function to this function. So that would be the localization function at the point. So note that here everything depends on the point on the curve. So you can imagine, so this works. So any x inside this one space. So therefore you can just assemble them together to obtain a function between shape of categories. Namely, you obtain a function from this KLG to P of bound G is this vector. So here let me say a little word about this notation. So first, whenever I use this underline I mean, so it's a shape of category over run or something similar to run. In other words, this is something happening in shape type of run. You can also call it crystal of categories because run is still run. Also, here this underlying vector means it's the constant shape of category whose fibers are just the vector. So in this lecture, you use the notation P mod 1, but I find that very confusing, and you'll just use this notation. So here, this KL underline means the shape of category whose fibers are KLX or some X. So note that this is an example of local to global functions. So the source is some shape of categories on one, and the target is some constant shape of categories. So a local to global function can be it's just a fancy word to say it's a function between general shapes to constant shapes of categories on one.
So this minus bond, you know.
Not yet. Yeah, so I will soon come to that. So here, so it's easy to imagine. So these node functions they can be glued together to get a function in shape category 1. But I claim it is even in shape type one unity. This is a very important point. So therefore, let me first tell you what it means. But I will not prove it. I will leave it as an exercise to you. So recall, what's the meaning of a unital structure? It means the following. So whenever you have points x and y inside the run, such that x is contained in y. So this is for x contained in y as points inside this run unital. So whenever you have such an inclusion, so you should add a function from your fiber at x to the fiber at y. So you should provide this function, so which gives you the unital structure on KL. And we know what's this structure. So yesterday, I think Yifei or Kevin told us that this is given by inverting the vector body. So let me say a few words how to describe this function. So this KLGY, so by the factorial property, so it's just the tensor product of KLGX. This KLG supported the complement subset Y matrices. So therefore, so to describe this function, we only need to produce something inside this tensor product. So and for the first factor, you just do nothing. And for the second factor, you just put some vacuum representations there. And if you forget what's vacuum representation, we will see it later. So but now I'm just saying, so we put vacuum representations for the points away from X. And this is the unital structure given by KL. And if you forget why this is the unit structure, so yesterday Kevin justified this unit structure has to be related with disks and puncture disks. In some sense, that vacuum is the induction from disk to puncture disks. And on the right hand side, so it's just a constant shift. And for constant shifts, the unit structure is always the trivial one. So in the sense that the fiber at X is really just d bound G, and the fiber at Y is also d bound G, and it has to be the identity functor because what else do we have? So therefore, the claim that this is a functor contained in this two category means the following diagram commutes. So this commutes. So for any inclusion. And I will not prove this. So instead, I will give you as an exercise. So this exercise can be proved in millions of methods. So for instance, you can write them as some push, and then this is really just some exchange with an exercise. Or if you remember the calculation done in Sam's talk, where he calculated the image of vacuum. So by using the compatibility between induction functors and lock, so then you will realize this follows for something happening already for cubicle. So anyway, this is left as an exercise to you. So any questions so far? That again? That's bad. Remember that. So vector is just a category of vector spaces. And it's a DG category, so when I draw this under that, I mean you view it as a base of categories over the vectors. As a constant base of, in other words, at any point, the fiber is the. Yes, because vector considers any DG category. So, okay, so this is the unit structure for lock. And now let me produce this functor. So to distinguish between these two things, from now on, whenever I use this notation, so a functor with an underline, I mean, it's a movement between trace of categories, and when I use just look without this underline, I mean the following. So it's the following computation. So you look at the source and you take its global section on run, so which is some category denoted by this KOG run. So it just means at any point of this run, you should provide a module inside this KOG, and they should depend algebraically for these ports. And by functionality, so we can apply this lock underline and take its section at this run, so you get a functor from this thing to the global section of the right hand side, which is just d of bound G times run. So because the global section of the constant shift would give you d modules on the space. And now we followed by taking direct image along this run direction, I will denote by integration for run. So some people might say taking this fraction homology, but not yet, because we don't have a fraction algebra. We are just taking some d modules on run and we do this integration. So this is the functor there. So this is the localization functor. That's the reconnection for KL. So any questions so far?
So this integration one is just the raw force.
Yes, because run equals to run the run. It's really taking the homology of the sheet. So by the way, let me give you an exercise. So knowing this functor, this log, is equivalent to knowing this Morphinum control of categories. There's no content. So the data containing them in them are the same. So which is really just some technical thing. Now let's come to the second recollection. So I will remind you what's this for F step. And also that for F back. So let me first remind you what's bit from F. So here we use bit shrink. So because we are talking about invariance, so you consider the category of all the modules on the F cross mining for this point, and you put some invariant condition, equivalent condition for shifts. So namely, you require to be equivalent with respect to the loop group to N, but against a character K. And this character is the character, is the, in some sense, unique non-degenerate character. So this category was defined in Andre's talks. And let me define this for a functor. So we have mapped from this F cross money to bound G. So namely, you can view this as a space and of cross money which classify G bundles on the curve trivialize away from the point. You forget the trivialization, you get this map, we call this map pi. And using this pi, we can do direct image and pull back. They are adjoint to each other. So therefore, the induce an junction between two categories, the source is bit and the target is P of function G. And the left adjoint is just given by pi lower shrink. So but you need to justify this function is well defined. And the right adjoint is given by you first shrink pull back to get something under G, and then you do averaging against this Whittaker condition to get something inside this Whittaker category. But you have to justify this function is continuous. So this has been explained yesterday, and we noted these functions by concrete shrink at x and for f star at x. So these are the functions between bit and boundary. So any questions so far?
You just run it on that sort of for the very beginning. Yield and D is constant as well, right?
This is really just a plain category. You put no structure here.
Yeah.
So therefore it's like you tensor a constant shift with a vector space. So this is a categorical vector space, this is a categorical constant shift.
Okay.
So in other words, if you look at the entire thing, it's still a constant shift whose fibers are given by
So you're mapping out of the sheet into constant sheet so you can map out of the
yes. Yeah, exactly. Okay, so let's come back to this. And you can imagine, so these things are compatible. These things can be assembled together to obtain a function to shift of categories on one. So according to my notation, so I will know this adjunction like this. And the right adjoint will be this for F star on the line, and left adjoint will be this constraint shrink in the line. So note that this constraint shrink on the line is it's a local function. So the source is something local, the target is something constant. But this for F lower star is some global to local function. So it's from some constant thing to the constant to the non-constant thing. And here maybe someone would ask some question.
Maybe you should say unital.
Yes, you may want to talk about the unital structures here. And to do that, I have to first remind you what are the unital structures on this sheet, and then try to see if the diagram commutes. And surprise, surprise, so the right adjoint is not unital, it's only right max unital. Okay, so let's
Is this averaging thing is the right adjunct?
yes, So whenever we write ab lower side means right adjoint. Ab lower shrink is the method. Okay, so now let's talk about the unit of structure. So first, I claim this bit shrink G has a unit of structure. Instead of telling you how to do it in a precise way, I will tell you what's the unit factorization algebra inside this bit G. So in other words, I will tell you what's this function. This is the unit. So in other words, I will tell you the unit object rather than all the hard compatibilities. So what does this object do? So let's look at GER G. Inside GER G, there's something called GER of n. It's just the nk orbit for the unit section of this GER G. And this GER of n actually maps to G of GA. So in a way that is compatible with this character chi. So recall this is some character on loop of n, and this GER of n is a quotient of that. So that character actually factors through this GER n. And now you can pull back the exponential shift here. So to get some exponential shift on the GER of n, which I'm just abuse notation, and consider this map, let's call it P. And you just do this P lower shrink of X to this shrink extension. So, and the claim is this unit factorization algebra is given by this P lower shrink of exponential shift on this GER of n. So this is a claim. So you have to justify it by showing that you can actually define these things in families and verify all the compatibilities. But in some sense, it's kind of easy to believe this. So because of the following, so if you look at just D modules on Avant-Grassmann, it's easy to believe the unit is given by delta shift supported at the unit section. But now we want something contained in the Whittaker category. And we cannot just look at this delta function, delta shift, because it's not Whittaker invariant. And you need to make it Whittaker invariant. So there are two ways to make it. So either via some shrink extension or star extension. And you will soon realize that at least pointwise, so these two are the same because of this cleanness statement made by Edwards.
Ja, maar n is twisted, right?
In what?
N man.
Yes. Yes. Yes, a little sheet. Yeah. Okay, this is the unit of factorization algebra inside this bit G. And let's pretend we already know the entire unit of structure on this bit G. Here, so to check if you understand what's happening before very nicely, so I will give you two exercises. So they can be proved by unwinding definitions. But for now, you can just believe me, and it tells you some information about these functions, which will be used later. The first thing is kind of easy. It tells you that this unit admits a right adjoint, so which is really just given by the fiber of your Whittaker sheaf at the unit section of this Grassmann. This is kind of something easy. I'm just telling you there exists a right adjoint, and I gave you a formula. And the second thing tells you that how this unit thing is related to Cashman-Schleicher. So let's consider this weak shrink G, and we consider this G check. We also view it as a factorization category overrun. And I think maybe Nick or maybe Kevin explained to you that this thing is a unit of function category. And this Cashman-Schleicher, so we defined before, is actually an equivalence between unit of function categories. And therefore, you might expect, so the following diagram commute, and indeed, so here, this is restrict to the unit section, go to vect, and this is given by, just forget your G check structure.
variance.
The variance.
Oh, sorry. Oh. Yeah, of course. Yeah, it's whole out of tree. It is in. So now let me define what is this what is this coef vacuum? And I will say more words about it. Now we consider the only combination. It's similar to what we did before. So we start from D of 1G. So we first pull it back to D of 3G times this one space. And then we do this for F overrun. So we go to some big sweep G1. So this combination is the coef function on that one. So this is the coef equals star, which is a function from D bound G to the run section weak. And now we can further go down. So we first apply this run return. In other words, we just do the fiber at the unit section. So you will get just a plain vector space, but spread over run. In other words, you get a d module on run, and now you do this integration on run to go to something vect. And let me call this function for f vect.
No, but when you do, before the integrate, you already get something constant. Well, anyway, you can do this for yourself because you don't have to. This.
Yeah, but I want to do this.
Okay.
So because look that this combination has the following feature, it's really kind of something introduced by Nick. So you first reserve vacuum for this constant family. So here for constant family, so this unit is just the vector space K itself. This is like invert vacuum. This is like apply your vacuum function, and this is like doing integration. So in other words, you may say this coef back, which is a function between these things, it's really just given by applying this formula to this next unit of vacuum function. So that's some exercise for you. But as Danny said, there are many other ways to describe this function, and I'm going to tell you. So the first alternative description is using global geometry. So I will show you what it is, and if it has an exercise for you to show that they are the same.
But let's do it before, just that you can write. When we suppose the first three functions, you already get something constant. Okay, we'll see.
So the punchline is this coef underline is a right next unit of function. So you can take a section and empty. And what's that function? One is by definition, it's this C. So this is the way to define this purely without choosing any code. Yeah, it's not necessary, but I'm just doing it for fun. Now let me give you the actual definition. So which using global geometry, and that is the definition we will use when we prove these things. So if you get confused by this, just ignore that. I'm just doing it for fun. So the actual definition was actually given by on Monday, and to verify that the same, you need to do some polynomial shift and some twist. Let's ignore them. So from now on, every diagram is commuted up to twist and shift. So this exercise tells you alternatively, you can define this function as follows. You consider the following diagram. So here we have this function G, and it receives a map from this function omega, namely point P, and there's a map to point in Q, and there's a character to this GA. And this function is given by pull twisted by exponential shift and push. So in other words, put it on the down, the upper shift, its tensor with this term which is. So that was the definition given by Sam on Monday. So and that's the definition we will use when we prove 6. So the content of this exercise is to compare this global definition with the local definition. And to do this, so you have to compare this bar n omega with something about curl of n, and let me give you a hint about this. The map from curl n to bar n is actually, this map actually has comparable factors, and you can use that fact to compare it. So let me give you some advanced exercise, which is the functional for my approach to this function. You might not solve it without revisiting this lecture. So the first thing is kind of easy, it says that this concrete shape is uniform. So the second thing is a little bit harder. So it tells you like this for F, lower star is right next to unity. So in general, you can even prove whenever you have a unit of function F, it's right adjoint, pointwise right adjoint. If it exists, it's a right next unit of C. So it's indeed true. The second thing is, as I said, if you have a unit of next unit of function between crystal categories, you can take its section at any point on this unitogram. And recall on this unitogram, there's some very silly point called the empty point. So the section of this function at the empty point, here this empty is a point on this unit point. I claim, so it is a function by definition from E of bar G. Recall this E of bar G is viewed as a concentric fiber at any point of E of bar G. To the fiber of B at the empty point. What's that? What's the fiber of B at empty point?
Yeah.
Yes, because you are considering alpha gross mining for low point. There's no data, so it's really just a point. You consider Whittaker condition at a point, so which is really trivial. So it's a function of vector. And this advanced exercise asks you to verify this function is given by a curve. Okay. So if you think carefully about this statement, you will realize that follows from something big topic. So namely, yeah, so I will not spoil it. So you should try to exercise by yourself, and if you get confused, you can ask me. So okay, so far for these recollections. Oops. Any questions so far? We look on time, but still want to know. Now let's come to the main statement of this lecture.
I have a question that you might address. For Yale, lock and explains what like the climate and points, kind of doing something way, like yes, it's very explicitly module. So are you gonna tell us anything about flavor?
No.
Right.
Can I just make one comment about the here?
So we can't, that's not because it's like we decided what was new.
It's completely the same. I'm still gonna say it just in case people are confused, because the whole point of this exercise too is that it's not exactly true of an empty set down here. Like sometimes you need to choose that one point down here is the top.
So that's
Doesn't work for the empty set.
so people understand it's irrelevant, doesn't work.
Yes.
Yeah.
Okay, let me tell you what's the main theorem for this lecture. So as promised to you, so we want to calculate the composition of the following functor. So we start from KLG1, which is the global section of the shape of category. So we take the local to global functor to the object. And we apply a global to local functor so to this bit trick. But unfortunately, so we can't do that. Now, so what we will do is we will do an easier one. So we will do the first step, which is this for f back. So we will calculate this composition, and I will tell you the answer. So you will soon recognize it's very similar to some construction in Nick's lecture, and that's the reason for his lecture. So we first insert vacuum for this KOG. So let me remind you what's the domain of this function. It's the section of KOG on this run subset. And let me remind you what's this run subset. So this classified pairs x containing y. So here x and y, so there are points inside this run. So viewed as final subset of your curve. So it has two projections to this run space. So one is called PR small, which remember this x. The other is PR big, which remember this y. And now, so along these maps, you can pull back any shape of categories you like. And if you have some C here, if you have some C in let me write shift cat on this run. So you can just pull it back and on this big map. Yes, it's the big map. To get a shape of category on this gadget, and then you can try to take global section of this. And I will call this global section run subscript subset. This is the meaning of this notation, and we apply it to the case when C is KL, we obtain that category. It's really just a category, it's not a shape category. And this unital structure of KL allows you to produce the left vertical functor, so which was extended in this talk. And this is the first step. And the second step is to apply some functor called trivial Sokolov reduction. So I will remind you what's it. But it ends in D modules on this run subset. And the last step is to do integration on this space. In other words, the taking of homology. And the claim is this diagram commutes. So this is the statement of our main theorem. And modulo the definition of the TF. And I'm about to give you the definition. But before that, any questions?
Yes, so this modification of run you wrote, that's the space of like one synthesis in the run you took, right? Yes.
Yes.
Okay.
So if you want, you also have a version of this result of this run replaced by run unit. People somehow do not like the section or something on run unit, so they use this. Okay, let me remind you what's this DS. the straightforward circle of reduction. So it was introduced in reverse talk. So I will give you first remind you what's in his lecture. So if you have some n, which is a module in KL, so say support at the point, so this thing is given by so-called semi-infinite cohomology. So with respect to the loop in the algebra for n, here n is the important radical of your barrel, but you need to remember this group thing, so you can simply ignore that. So for this n, but you need to make a twist. Here, this twist is because you are doing Whittaker. So we twist it by this counter cap. So here, this is a one-dimensional representation of Ln. So therefore, you can tensor it with n to produce another representation. And Gruber says that this is a hybrid of cohomology and homology. Namely, it behaves like cohomology, the algebraic cohomology for this group, and homology for the quotient. It doesn't really make sense, right? So therefore, I will make sense of this by giving you the formula. But this formula only works at a point, but at least it gives you some feeling about this formula. And if you want to do some calculation, you can play with that. So we write this loop n as a union of group schemes. Here, the word is really scheme rather than scheme. So in other words, we want these Ni to be schemes, although they can be like interdimensional. So for instance, you can declare this Ni to be some adjoint image of this R group. Namely, you can do this. You consider minus I rho, t to the minus I rho, you use it to act on this R group. You get some Ni. And you can check that the union of all these things is this Ln. Note that here I'm really cheating because this only works for Leopoldine groups. If you want to do semi-infinite cohomology for G, you cannot do this because you cannot write Lg as a union of group schemes. So this is really a cheating for Leopoldine ones. So now let me give you the formula for this. I will ignore this twist because it's not important. So it's a colimit of some cohomology. So this colimit is indexed by the by I. Here you got this Ln as a unit of Ni, but you can verify that the result, this colimit does not depend on how you write Ln as the units. So of some cohomology for the algebra of this Ni, so which I denote by this small sign. For some module, but this module is not just n. You need to produce a shift and twist. So let me first tell you what's this twist. So twist means you tensor with some line. So it's the determinant of the quotient of Ni by this N0, so which I mean just this R group, the algebra of this R group. So you can safely ignore this factor if you are not interested in the weight spaces of this. So you can only see this factor if you look at the weights. So but there's a coordinate shift by the dimension of these things. So this is the coordinate formula of that. If you have never seen this twist before, so I encourage you to compare the algebra cohomology and the algebra homology. And you will see that there's some factor like that, which explains why this gadget behaves like cohomology for N0 and homology for the remaining part. And it is this formula that realizes what Gabriel told you that semi-infinite cohomology is like a hybrid of cohomology and homology. Okay, let me give you an exercise. If you have never seen this before, it's very quick. So to define the connecting maps so that you can make sense of this coordinate. So So far, we defined the central circle of reduction at a point. Any questions so far? Okay, so now let's continue. So because this thing depends on disks and puncture disks and use nothing more than that, you may expect that this functor can be upgraded to a functor between shape of categories. So in other words, you may want to obtain a functor from this shape of category to just vector underline to this constant shape of category. And this is indeed the case. So, but to actually realize this, you need some homological algebra method. So let's believe this. So we have such a functor, and you may wonder whether it's a unit functor or not. So now I claim this is only a next unit functor. So it's the general phenomenon. So if you have some cohomology, it should be next unit because it's some right adjoint. But here we are doing some cohomology mixed with homology. So you really need some argument to do this. But just believe in me, so this is a next unit functor. And there's a way to see this. So namely, we know what's the image of the unit factorial algebra under this ds. Namely, so the unit factorial algebra in KL is that. And we want to calculate this ds of that. And that was done in E-phase talk. And we identified this guy, this Z, which is really the center of that. It's also the global functions on opus. And therefore, you see that it does not send unit to unit because the unit in vect would be the trivial thing. It would be the one-dimensional vector space. Instead, you get some algebra. And because this is some algebra, so it receives a map from the trivial factorial algebra, which I denote by 1, to it. And therefore, you see this is only at most the right next unit. It cannot be unit.
I think the quantitative mixed up is that integral functors from some local thing to some global thing, those should be thought of as typically being of very global nature. And this functor is clearly a very local nature, so it shouldn't really be a shock that it wasn't a local functor. That it's not usual, aka a local functor.
Then I have a question. So we read kind of we read your talk to we can't solve it. So the question is, you have to if you have to spill over. The question is whether you want to make a break.
Okay, so I will run some exercise and then we will. So this exercise is almost trivial if you amend the definition. If you get stuck, you might want to revisit mixed talk. So I will call it topology. So let's look at the combination, this main theorem. So you insert vacuum, apply this ds over this line subset, and then doing this integration. And then there's another way to write it. So namely, we consider the so-called ds enhanced. Let me remind you what's this. So it's a functor from this KOG to factorization modules for this D. So here we are using the general paradigm in Link's talk. So suppose you have some F between factoring categories C to D, and suppose it's only right next unitary, then at mass factors rule the following thing, you consider F unit of C, so I will write just 1C, and you consider it as a function algebra inside D, so you can consider its function modules. So a program, these modules are supported at some points, but you can make these points to move on run and form a shape of category on run, so therefore you are allowed to put an underline under it. So the claim is this F always factors rule this category of fraction modules, and this is people called F enhanced, and this is just forgetful function. Here, forgetful means you just pick the fiber at the marked point and do not remember the algebra part. So then, in general, for next uniform function, you have such a thing. And because this ds is a next uniform function, so you can produce this ds enhanced. So this is function 1. So any questions so far? So function 2 is doing fraction homology. So let me write it. This the first one is uniform. So in fact, you can show this thing has some universal property. Is the so this F enhanced is the it's the closest category to see such that this function is unique. You can make sense of that. Yeah, I'm going to describe a function from this guy to back to you. So if we pick a point on this line, so we want to produce a function from function d mod to back, and this function is taking function for homology. There's no function for homology. So its function homology will occur with respect to this algebra, and the coefficient is your model. So this can be defined on any point, any marked point, and when you put them together, you obtain a function between shape of categories. And you may wonder whether or not this is unital. Of course, it's not. If it's unital, it sends something to the one-dimensional vector space, which is unital. It's not unital.
Oh, which one? Which one is you? Factory suppose you forget or you don't get it.
Yeah.
So I don't know which one you meant. I don't know which one to home.
I mean, factory homology. Yeah, so. Yeah, you can also use forget.
Yeah.
Okay, here the exercise is ask you to rewrite this combination as the following combination. Yes, I will start going. And then we will take a rest.
But if you check if it's unital, we need to evaluate this on Z and 6% one dimensional. So
Yes, but it's a yes,
I don't know what else is proceeded.
so if you have some m, so you get some vector space. You can also consider m box with d, you get another vector space. Then these two vector space are the same. Yeah, m box d means fraction modules for that two points. So this combination is given by the following. You consider this KOG. One. So you apply this trivial enhanced or trivial total enhanced factor to get some to get the section of this d mod fact over 1. So this means it's some fraction module supported at 1. So in other words, so the entire module structure is exhibited by something on this 1 substrate. That might be our conclusion point. But we possible. So then you apply the global section of this fractional homology. And then you do this integration back. And claim is this combination is given by that combination. So this it's not complete topological, but it follows from something big totals. And if you get confused, you can come to us after the talks. Okay, and now I'm ready to take a break.
So okay, let's so we this has a lot more important material to tell us. So how long do you think we afterwards? Realistic? No. Yeah, we have only 2 talks happening so please sort of.
I can try to do it in 40 minutes.
Yeah.
Maybe even
So
30.
let's have an extended break.
Yeah.